Welcome back everyone. In this lecture, we will actually state and prove Burnside's lemma. Okay. So, if I get time, I will give some applications of Burnside's lemma in combinatorics. But anyway, it's a very important lemma that actually tells us how to count the number of elements in the set of orbits. So let's start with fixing some notation. As before, let's say G is a finite group. And let's say it's acting on this non-empty set X. Okay. So, because we are interested in counting problems, we assume everything is finite. Okay. So, G acts on this non-empty finite set capital X. Okay. So, then recall this X mod G denoted as the set of all orbits. The set of all orbits of capital X with respect to the action of capital G. Okay. So, recall what is an orbit. So, given X in capital X, the orbit of this capital X is all possible images of this X, okay, under the action of capital G. And then we proved that this orbits, okay, for the distinct orbits form a partition of this capital G, and then we denoted this X mod G by the set of all orbits. Okay. So, sometimes we are also interested in counting the cardinality of this X mod G. Okay. We will actually demonstrate this with using some examples, okay, mainly coming from these coloring problems. Okay. But anyway, let us try to understand what happens to this cardinality of X mod G. So, let me state the result. Okay. So, even though it is called actually Burnside's lemma, so this was actually first proved by actually Cauchy. So, sometimes people make a joke about this lemma. So, this is also called not Burnside's lemma, because Burnside was attributed for this lemma wrongly. Okay. So, but Burnside's in his book actually quotes Frobenius is the first one is proved, okay, this lemma. But even before that Cauchy actually knew this lemma. But anyway, what is the statement of this lemma? So, this is a very basic lemma that counts the cardinality of this X mod G. So, the cardinality of X mod G is given by, so 1 divided by the cardinality of G times the summation the cardinality of X power G, where G runs over capital G. Okay. So, now recall, so what is this X power G? So, this X power G is nothing but those X in capital X such that that is fixed by this G. Okay. So, X power G is a subset of X. So, this is those X in capital X such that that is fixed by this G, given element G. So, this is a important definition. This is something comes up very naturally. Basically, this X power G is a invariant subset for this action of the subgroup that is generated by G. Okay. So, those sets naturally appear when you want to count this X modulo G. Okay. So, how one actually attempts this lemma? Okay. This lemma is basically is an application of counting two ways. Okay. There are these results that one can prove in combinatorics. So, many identities, for example, they prove by counting the same set in two different ways. So, that is what we do in proving in this lemma, proving this lemma. Okay. So, let us see like what I mean by actually counting in two different ways. So, first recall from elementary matrix theory the following fact. Okay. Let us say you have some n by k matrix. Okay. So, let us say you have n by k matrix. So, this n by k matrix has entries, let us say 0 or 1. Okay. So, you have this n by k matrix, let us denote it by capital A. So, which is just given by Aij, this is just n by k matrix. So, assume that Aij either 0 or 1. Okay. So, we will choose, we will assign the value 0 or 1 depending upon some particular data, but let us say this is what given to us. So, then the matrix going to look something like this. Okay. So, it is going to be 0 0 1 0 0 and then 0 1 1 1 0 and so on, let us say some 1 0 0 1 0 something like this. So, this is 5 by 3 matrix. Okay. So, what is important think about this matrix, one can talk about row sum as well as column sum. Okay. You fix one row and then just sum all the entries in that row. For example, here we get exactly. So, these are all the first row sum, let us call it R1 and this is R2, this is R3. This is the first row, second row and third row. So, what we are going to do, we just take all the entries in that row, just sum it. Okay. For example, here we get 1, here we get 3 and then here we get 2. And similar to that, we can also sum all the columns. Okay. This is the column 1, column 2, column 3, column 4, column 5. So, then you can actually sum all the entries in the columns. For example, if you sum the first column you are getting 1, the second column you are getting 1, third column you are getting 2 and fourth column you are getting 2 and then the last column you are getting 0. So, what is row sum? Row sum is going to be sum of all the row sums that you got. Okay. This is just ith row sum. Okay. So, you take this R1 plus R2 plus R3. So, that is going to be your entire row sum. Okay. So, that is exactly what? That is exactly you can see that is 6. If you think about it, this is going to be exactly the row sum is nothing but sum of all the entries. Okay. This is going to be sum of all the entries, but this is like you are fixing I and then summing over j. So, it is basically writing in two different ways. So, you first sum over I and then sum over j. Okay. So, this is what row sum, but this is all finite sum. This is exactly equal to summing over j and summing over I. So, then you get this. So, this is exactly your column sum. Then you can easily see that the column sum again adds up to 6. Okay, 1 plus 1 plus 2 plus 2. So, that means the entire row sum is going to be same as entire column sum. Okay. So, this is exactly what I was actually telling. So, counting a set in two different ways or counting some sum using two different ways, that is going to give you exactly the same answer in combinatorics. Okay. So, that is what proves this equality. So, this equality we rewrite in some different way and then we will see that this equality really comes from counting same thing in two different ways. Okay. So, how one can actually look into it. Okay. So, the only key thing that is there in this result is this equation g dot x equal to x, and of course, g comes from capital G and x comes from capital X. Okay. So, this equation, so now you can fix x and vary g. Okay. So, that is the sum you are seeing here on the right side, which is the cardinality of x power g, g in capital G. Okay. So, you are fixing g and varying x. So, that is going to give you exactly the cardinality of x power g. So, now if you vary over g, you will get this summation. Okay. So, you get exactly this sum to be the cardinality of all those g x coming from g cross x such that g dot x equal to x. So, what you do? So, how you do this counting? So, fix G and vary X in this equation star. Okay. So, then you are going to get X power G, that is those X in X such that G dot X equal to X. So, that means you are going to get exactly the cardinality of this X power G. So, once you fix G, so this many elements you are going to get. So, now if you vary G in G, so then you are going to get summation X power G, G in G. Okay, that is the counting that you get. So, now we can do this other way. So, how one does? Now, you can fix X and vary G in G. Okay. So, you can think like this. So, now you can see that now you fix X and just vary G. So, then what will happen? If you fix X and vary G, so that is going to be just the stabilizer Gx. Okay. So, you are going to get Gx. So, that is those G in G that fixes this X. So, then you are going to get the cardinality of Gx, that many counting. Okay. So, now if you vary X in X, so you are going to get summation Gx X in capital X. Okay. So, basically you are saying that these two summations are equal. The summation mod X power G, G in G is exactly equal to summation mod Gx X in capital X, which exactly counts the number of G comma X in G cross X such that G dot X equal to X. So, that is why these two summations are equal. So, basically counting the same set in two different ways. So, let us do it more set theoretically. I will also give you actually matrix proof. Okay. So, let us first do it set theoretically. So, what we are trying to do, we just take all the tuples from G cross X such that G dot X equal to X. So, now this can be realized as disjoint union of first of all X power G, G in G. So, there is a natural bijection. What is that natural bijection? If you think about it, so given Gx, you just map it to that element. So, what is X power G? Okay. So, the X power G, okay, you fix G basically, that is what I am saying. So, X power G is those X in capital X such that G dot X equal to X. So, in particularly you take this G comma X and then simply map it to X inside X power G. Okay. So, that is the map, and that map naturally defines bijective correspondence between these two sets. So, now you have another map. You can also take this G comma X and then send it to G in Gx. Okay. So, that is going to define a map from the same set, okay, from the same set to disjoint union of Gx X in capital X. Okay. So, now by composing these two maps, you get bijective correspondence between these two sets. So, that is what this counting says. Okay. This is purely set theoretical proof. So, let me actually give you actually matrix proof, which is much more visible. Okay. So, what you do, you can actually index this G cross X as indexing set for the matrix. Okay. How do you do this? So, you first list capital X as some elements x1 etc xk, and then you list capital G as these elements G1 etc Gn. Now, look at this n by k matrix. Okay. So, where the entries are actually given as follows. Look at delta comma ij, this is the ijth entry, that is given to be 1 if gi dot xj is exactly equal to xj, 0 otherwise. Okay. So, what we are looking at it, so let me write it very clearly. So, your columns are given by, let us say x1, x2 up to xk, and the rows are given by g1, g2 etc. gn. So, basically this is n by k matrix. Okay. So, these are all rows. So, these are all columns. Okay. So, now if you look at this particular entry, okay, so this is going to be just g1 dot x1. Okay. So, either it can be actually x1 or not. So, depending upon that you put value either 1 or 0. Okay. So, if you look at this g1 dot x1, g1 dot x2 and so on, g1 dot xk. So, what it does? So, g1 act on this x1 etc. xk, it just permutes. Okay. So, this g1 dot x1 etc. g1 dot xk, that will be again listing of this x only in some other order. Okay. So, we want to look at those elements that are actually fixed, that means it should never change. Okay. For example, if xi is here, then this g1 xi we want it to be xi. So, it should not be changed. If it is not changed, you put 1 there, you put 0 otherwise. Okay. So, that is what we are doing. So, we are filling this matrix using the entries of this delta ij. So, the delta ij, what it does, if it is in the correct order, that means gi fixes xj, then you put 1, otherwise you put 0. Okay. For example, let us say xi is x2 is fixed, you put 1, otherwise you put 0, like that, you put 1, otherwise you put 0. Similarly, g2, if it is fixed by, if it fixes x1 you put 1, otherwise you put 0, like if it does not fix xk you put 0 and so on. So, that is what your entries. So, delta ij is nothing but 1 if it fixes xj, 0 otherwise. So, then what will be the ith row sum? Okay. If you look at some particular ith row, so this is going to be your ith row, let us say this is the ith row. So, let us say the ith row sum is Ri. So, Ri is just sum of all the entries in the ith row. So, let us calculate what it is, ith row sum. So, this is going to be exactly the number of j's, okay, the number of j's from 1 to k such that, so gi is maps xj to xj. So, that is exactly your ith row sum, because you are putting 1 whenever gi maps xj to xj, otherwise you are putting 0. So, it is going to count all the j's such that are fixed by gi. Okay. So, now if you take the row sum, then what will happen? The row sum is going to be sum of all ith row sum. So, that is going to be exactly equal to summation all this. Okay, this is something what? This is exactly equal to, so you have fixed I and then varying j. So, that is exactly, it is x power gi. So, this is x power gi, this is I range from 1 to n. So, this is I range from 1. So, that is exactly your row sum. Now, if you look at the column sum, what happens? So, let us say you are looking at this jth column sum, jth column sum. So, that is going to be the number of now i's 1 to k, sorry 1 to n, such that g, now j is fixed, gi is varying, xj should be exactly, it is the same equation, but read it in the column way. Okay. So, you are taking some column, okay, let us say the jth column and looking at that particular thing. So, then you will have 1 whenever some gi fixes xj, otherwise you will have 0. So, that means this thing is exactly equal to the cardinality of. So, because j is fixed, I is varying, it is exactly g x j, because it is the stabilizer, because you are looking at all possible elements of g that fixes x j, which is the stabilizer. Okay. So, that means, so the column sum, okay, is going to be the column sum is summation j from 1 to. So, how many columns are there? There are k columns, g x j, the cardinality of this. Okay. So, that is why because the row sum is same as column sum. So, whatever you have here is going to be equal to this. So, that indeed says the summation x g g in g is same as summation g x x in capital X. So, this is what is. Okay. So, now we will use the orbit stabilizer theorem to rewrite what is happening here. So, okay. So, let us do that computation. So, let us start with this summation x g, which is there on the left side. So, which is same as summation g x x in capital X, that is what we proved. But using the orbit stabilizer theorem, you can see that this is summation x in x, the cardinality of g divided by the cardinality of the orbit g dot x. So, note that g dot x is nothing but the orbit O x. So, in particularly I can take this g out, then I can write this summation into two different summation. So, the orbits are same if and only if this y is conjugate of x, okay, for some g in g. So, that means x and y come from the same orbit. If x and y come from the same orbit, then the orbits are same, okay, that is the only condition. So, that means I can run this over all the orbits, okay. This I can rewrite, this capital X is written as union of orbits. So, I can write this as sum over all the orbits, and then x is coming from the orbit divided by, okay, 1 divided by the cardinality of the orbit. Okay. So, this if you rewrite, you can see that the cardinality of g is exactly equal to summation the runs over all the orbit times. So, this is all the cardinalities of the orbits, the 1 divided by these are all the some fractions, they are all equal. Okay. So, that means this is going to be exactly the cardinality of the orbit divided by the cardinality of the orbit. So, this is going to be exactly 1. So, then this tells you that this is exactly the cardinality of g times the cardinality of x modulo g. So, indeed you have proved that the sum of these things, summation mod g x x in x, is exactly equal to the cardinality of g times the cardinality of x modulo g. So, then this proves that if you rewrite the cardinality of x power g, g in g is exactly equal to the cardinality of g times the cardinality of x mod g. So, from this you can easily conclude that the cardinality of this x mod g, that is the counting the number of elements in the orbit, is exactly equal to 1 divided by the cardinality of g times the sum of all this mod x g g in g. Okay. So, these are all the sums. So, in case if you know some information about the set that you are interested in, okay. So, okay, this x power g for g in g. So, and in some sense if you know all information about the group, then you will be able to compute the number of orbits that that you are interested in. Okay. This is very important formula. and there are many generalization of this formula that are available in combinatorics. So, for example, this Paulias counting or enumeration theorem is also one such generalization. Okay, so but we will not have enough time to see some generalization of this, but I will try to do at least one concrete example that actually demonstrates this result. Okay, but this is actually, like I said, it's application of counting the same thing in two different ways. Okay, so using that you are getting such very beautiful formula. Okay, so the power of this formula actually will be evident once we start using this in combinatorics. So this is a very interesting result. Okay, so like I said, so Burnset is actually wrote down this result in his book, and but before Burnset, many people actually, like Frobenius knew this, and even before Frobenius, Cauchy actually knew this formula. Okay, so in literature this is quoted wrongly as Burnset lemma, but anyway, whenever you search for Burnset lemma in group theory, this is the result that you get. So this result, like I said, can be used nicely in order to compute some interesting sets in combinatorics. So we will see that maybe after proving the Seilos theorem, we will see some applications of Burnset lemma. Okay, I will stop here and I will continue with Seilos theorem in next class. Okay, so there are three theorems. So I'll state them and then prove them using only group actions. Okay, group action is a very powerful tool. So there are other proofs available. For example, one can use inductive argument in order to prove this. Okay, in order to prove Seilos theorems. But we will also see various applications of Seilos theorem. That those applications are very important. In particularly, we will be able to determine, okay, groups of small order, okay, up to isomorphism. So that will be kind of very important task in this course. Okay, and later we will specialize to finite abelian groups and then try to classify them up to isomorphism. Okay, I will stop here. Thank you.